Hello, and welcome to this fourth season of the CircPod, the bilingual scientific podcast presented by the Canadian Consortium for Research in Epigenetics, Environment and Health, hosted by the Student Committee. This season stands out from previous ones, as it is a special edition dedicated to scientists who have built their careers outside of academia. Through these episodes, we will explore their career journeys, research, interests, and much more.
I'm Ivana Sanchez, a master's student in bioinformatics at UBC, and I'll be your host today. I'm joined by my co-host, Laura Godfrey, a postdoctoral fellow at the Dana-Farber Cancer Institute. We'll be interviewing Dr. David Cheishvili. We hope you enjoy this episode. Welcome, Dr. David Cheishvili. He's a molecular biologist and epigenetics researcher with over 25 years of experience spanning academia, clinical trials, and biotech innovation. Dr. Cheishvili holds a PhD in biochemistry and molecular biology from the Hubert University. He has co-invented patents in cancer detection and epigenetic age testing, led clinical trials and research in epigenetics, and published extensively on DNA methylation and diagnostics. He is Chief Innovation Officer at EpiMedTech Global. He's affiliated with the Department of Oncology at McGill University in Montreal. And he also holds leadership roles at NanoWell Inc. and MTL Epitherapeutics Inc. Thank you very much for joining us today. To start, could you tell us about your current roles in the different institutions you are involved with and share your journey into science? What shaped your path along the way?
Thank you for this kind introduction. I'm really excited to be here and share a bit of my journey. And I'll start with my main role, which takes most of my time. I serve as a Chief Innovation Officer at EpiMedTech Global, where we develop epigenetic biomarkers for early disease detection. I also co-founded MTL Epitherapeutics. It's a Canadian branch of EpiMedTech, where we're marketing epigenetic lifestyle products like epigenetic age and other tests in Canada. Right now, actually, we are developing a prostate cancer blood test with the support of Quebec's Ministry of Economy, Innovation and Energy and the McGill University Health Center. So that test uses DNA methylation markers in blood, and we hope it can provide a more accurate alternative to the current screening methods like PSA or even imaging method like MRI. Lastly, I'm also affiliated with McGill Department of Oncology, where I'm collaborating on epigenetic biomarkers in cervical cancer. And beyond that, I co-founded Nano Wellness, which focuses on hydrogen-based wellness technology. So this is where I am today. Now, to answer your second question about my journey to the science, I think could be more interesting. Look back and how I began the journey was not straightforward. I always knew I wanted to be the scientist, and I always wanted to do the science. And the real challenge was finding a way to stay on that path despite challenges and obstacles and the problems. And as a kid, I was always curious, catching the frogs, dissecting them, digging, trying to build a little lab in my grandfather's basement. But to turn this curiosity into the career wasn't very easy. I always loved problems, but of course, problem solving. And honestly, if everything is easy and perfect in life is boring. So the challenge is the problems that make you think, and that what make you smarter. This is how the human beings evolved through the challenges and through the learning. So my own problems actually started back in Georgia. I studied biology there, but my first language was Russian. So, but after independence, the education system completely shifted, switched to Georgian. So I had to relearn the language and all the scientific terms just to keep studying. And on top of that, we had almost no resources. Most of the courses were theoretical, no practical, no lab, nothing. And I wanted to do real science. And I even tried that in the 90s. I tried to transfer to Moscow State University, which was the most prestigious university in the former Soviet Union. But without money, without connections, without paying the bribes, it was impossible. So I continued the graduation at Georgian University. I graduated with honor, but without opportunities to continue the graduate school. So then I moved to Central Asia. I left science for 5 years. I got married there, and later with my family, my wife and my child, we moved to Israel. So that's when I decided to try it again. And but again, the same language problem. I didn't know Hebrew, I didn't know English, and I had almost zero lab experience, and I had a gap 5 years. I didn't remember anything about biology. So at first I worked as a security guard and studied biology on my own using biochemistry textbook that I found during a security check in the student's trunk. So he gave me that book, and I was reading with vocabulary, biochemistry, basics. So that moment actually was for me beginning of my return to science. And again, it wasn't very easy. I'm not as young as I used to be. And also I was refused many times. I used to, I was told the science is not for me. And but learning languages, eventually I met the late Professor Aaron Razin. He's one of the pioneers of epigenetics, and he gave me a chance. And I worked on a rare genetic disorder called familial dysautonomia. And that became the subject of my master and PhD degree. Then I moved to Canada for postdoctoral training with Professor Moshe Schiff at McGill University. And this is how I entered epigenetic more fully. And actually it opened a completely new chapter in my career. And from that point, I am engaged with epigenetics, and epigenetic became the main focus of my research and of my life. But that's another story.
At the time, did you have any mentor or role models who influenced your scientific journey?
Well, I'm against the creating the model. So I didn't have any models. I actually, no, I love to read biography of the scientist. And I cannot recall all of the authors, but I loved to watch movies about the path of the scientists. There was a known Russian scientist. He's well known in Russia and Soviet Union, maybe not here. His name was Lomonosov, and he was coming from a very poor family. So to reach, and he wanted to be scientist. And so Russia is very big. So he was traveling. There was no cars, no trains to reach the Moscow. I don't remember either Moscow or St. Petersburg to enter the university. So I like the stories where the scientists are struggling to get something. That shows the science. And if you achieve the education, if you achieve, if you were able to get where you wanted to do, you will be also successful in science.
I think a lot of people will relate to different challenges while following a scientific career. How do you maintain motivation during challenging phases in your career?
Every new question motivates me. The problems motivates me. My family motivates me. Everything that opposing my thinking motivates me. So the challenge motivates me. Everything motivates me, but it should be something that challenging you. And every new question, again, as I said, if everything is smooth and there is no problem, the life is boring. So I love the challenges, I love the questions, I love puzzles, and the sciences are full of puzzles. That's what motivates me.
So you are currently involved in different roles, from academia to roles in the industry. What does a typical day in your life look like?
Mostly I work from home. My day starts with coffee, with a lot of coffee. That's the strong habit that I have. The secret is black coffee, no milk, no sugar. Because you don't want to, skip unnecessary calories. And actually, I've read that drinking up to 6 cups, it's a good for your health, for your heart, and other things. So without coffee, there is no day. This is how I start having coffee with my wife. We have 1 hour morning coffee time and talking. Every single morning, we start with talking and coffee and talking. And then I start. I go to my office and open my 2 screens and start working. I see a lot of numbers.
And how do you, you're affiliated with McGill, but also biotech as well. How much of your day is, or of your schedule is towards academia versus industry?
Look, I think that I can tell you that 4 hours I spend for academia and 4 hours I spend for industry. It's all everything connected.
Yeah.
And I think that both academia and industry, they have very different strengths. And when they work together, that results can be much stronger. And in academia, we focus on discoveries and publishing, providing something new. So something new for the scientific community. In the industry, the main question is, does it work and can it be applied right now? So for me, it's a very short path because everything is connected. Discovery from academia and asking the question, does it work or not? Can it be applicable? Can it be used as a disease prevention? Can it be used as a diagnostic tool? So it's very short path and everything is interconnected.
How would you prioritize what discoveries are promising for your current industry applications? I mean, there are a lot of research in the field. How do you select what type of results would be valuable in the industry?
Look, as I said, academia generates the ideas, right? That's the early data. What industry helps to refine and turn them into real product that can reach the patients. I've seen how projects evolve from early academic studies into clinical trials and real products. So that's kind of bridge we need more, moving ideas into practice. One good example, actually, if we're talking about the industry and academia, from my own experience, is our work on liver cancer detection. It started all as an academic project with international collaboration, but then it moved into clinical trials and now into product development. So this is kind of rich. So there is, it's not a question of priority. It's one step that require another step. The publication is not for the sake of publication. And in academia, sometimes I think we forget that the second question after publication, how we can apply this, how this can be useful. We spend millions of dollars of grants, right? But what does it mean? Can it be used in the real world? Can it help to the patient? Can it help to diagnose the disease early? There is no priority. Everything is priority. Academia, research question, and the real product.
That makes a lot of sense. And I guess a related question, a lot of people listening to this, will be interested in potentially moving from academia to biotech. So how was your experience with being a postdoc in academia and then kind of branching out and
You were in academia still, but also transitioning into the biotech space too. How did you do that?
Look, to be honest, I didn't plan. See, I don't plan anything in my life. Also, moving to academia, to the industry, I didn't plan. I didn't plan to go to industry. I stayed in an academic environment all through my training. And near the end of my postdoc at McGill, I was applying for a faculty position. That was kind of natural path, okay?
Wow.
And I was applying to positions in States, in Canada. But then my supervisor, Professor Schiff, he was launching biotech company, and he invited me to join. So that's how it started. At first, I even thought that leaving academia meant I wasn't really a scientist anymore. But I quickly realized that that's not true. What I saw in industry is that many important discoveries never go beyond the pages of the journal. I will repeat it again. The science shouldn't exist only for publication. Unfortunately, this is the trend that we see a lot. And that's the trend that we see papers are retracting because people want to get positions. People want to get good data. Without good data, you cannot publish in a good journal. And it's quite a big problem. So these publications should help people through these discoveries. And that's actually what motivated me to join the company. And later, the ventures like MTLP Therapeutics and Nano Wellness. So for me, industry is not departure of science. It's a continuation, just with a shorter distance between idea and the real world impact.
Now that we are discussing both academia and industry, and you're affiliated with McGill University, which is at the forefront of epigenetics research, but also being deeply involved in biotech innovation. So how do you see academia and industry working together more effectively?
I think through collaborations, and I think partially I answered your questions that the academia's role is more basic science. Industry is testing whether this science makes sense and that it can be used in the real world. I heard that many universities, actually the grant application, one of the requirements in the grant is what's the next question? How the discovery will be used? So again, it's not for the sake of publication. It's not for the discovery, for the sake of the discovery that will stay only in the lab, but how it will be used for the people. So these collaborations are important. I think it's already started. That's why we have the spin-off, right, in universities, that there's a good idea that you can commercialize it. So I think we have it, but we need more of that.
Do you think that that's changed over time, where maybe more classically, like years ago, that it would be more completely separate? You can see the transition to academia and biotech being a bit more integrated now.
I think so. And it's not the will to do that, but the life is changed. The economical situation is changed. Nobody wants to invest money into voodoo projects that won't generate anything. Everybody wants to see what's the final results, how these results can be used. And that's forcing both academia and industry to change the topic of the projects and work closely to each other. I feel so.
Is there any advice that you would give to a researcher, maybe to start collaborating in the industry too? Or what kind of advice would you give them to someone that is looking to have that synergy between academia and industry?
You know, the one example that I gave you, and actually I can give you a few examples. It's collaboration with the Department of Oncology, where we developed cervical cancer markers, epigenetic markers, based on a pap smear. That was collaboration with academia. But we as a company, I'm also affiliated with McGill, and I'm also affiliated with the company. So we run genome-wide study. We found the markers. What you do now with these markers? You need to validate them. You need to see them real patients, right? So we conducted the study. We took their discovery and we validated it in the lab. And then we created a product that can be used. So another example that I mentioned was liver cancer. It also started as a collaboration between academia and industry. It was discovery that happened in academia, that it was refined and adjusted in industry, and then the validation and the clinical study. So there is always need to collaborate tightly, these two bodies. It's very important that these bodies are collaborating with each other. And it's hard, sometimes it's very hard to see what's the difference between them. They are so connected to each other. If they are not connected, they should be connected.
Do you think biotech somehow, some companies now are becoming kind of like that in one, they have their own academic research within the company, kind of, they're doing research as well themselves. So do you think somehow biotech might still always need the academic collaboration, or might become more self-sufficient in themselves where they're doing kind of the basic research too?
This is an important question. I'll tell you what I think. The people trust more academia. So if you come from academia and you publish something, then the public in general, they trust. When it comes to the industry, the people are more skeptical because they will think, well, it's a business, it's a big pharma, this common, and that's a problem. So therefore, the industry always will need academia. From another side, the problem for academia that in many cases the publication are for the sake of publication. The student, PhD student, he doesn't care about how my discovery will be used in the real world. That's the problem for academia. So sometimes the project is finished. There is of course, we write in the papers in discussion, future directions, and this is typical, right? We say what we're gonna do with this study, what's the next experiment, but these are all words, right? What will happen in real life? How this discovery will be used? And here you have industry, because industry will take something important and can convert it to the product. That's why, again, we're talking about the connection between industry and academia. From another side, in industry, you can't lie. It's very difficult because when you do the validation experiment, and it should be validated before you do FDA approval or any other approval, that study will be validated many times, independently by different labs. So if the discovery is wrong, it will never be accepted. So you understand what's the difference and why both of the academia and industry are important.
From a funding point of view, from academia as well, I think external funding from companies to help with their research, you still get publications from that too. So it's, kind of almost a win-win situation for academia also from a purely...
Of course. I mean, if... Right. So if industry sees the potential, of course, it can be funded by industry. And if industry sees some publication in PubMed, right, and this publication is very important, of course, the industry will pick it up and will invest money into this. It's a really important product.
As you mentioned, it is very important to have in mind what the results of a research project, academia research project, will impact. Epigenetics, it's involved in aging and disease development, and it has an impact in our health. Like, how would you describe epigenetics and its role in aging and disease development?
Genes are the backbone, right, of our life. They're very stable. actually more than 99.9%, they're identical in all humans. So this tiny 0.1% difference explains things like eye color, hair color, but our difference not only in hair and eye, the difference go far beyond that, right? So we don't just look different. We also have different stress responses. We react different to the same food or medicine, or as you mentioned, how quickly we age. So that's because another layer of information on top of the DNA, which is epigenetics. No, think like of a piano at home, right? So the instrument itself had the same keys, the same strings, if it's acoustic piano. That's like your DNA. But the way the piano is played makes all difference. The notes are the same, but the music can be completely different, depending on the pianist, the style, and the mood. And that's what epigenetic does. So it doesn't change the DNA itself, but it changes the DNA, how the DNA is expressed, depending on lifestyle and environment. So DNA is like music notes, you know, and epigenetic is how the music is performed. Fast, slow, classic, jazz, pop, rock. That was what epigenetic does. So the flexibility, this flexibility explains why identical twins are different, right? They have exactly the same DNA, but one can end up in a different health condition and behavior. And but almost every disease study today so far, there is some involvement of epigenetics. In cancer, disrupted DNA methylation is considered as universal, not just side effect. It's a part of how the disease develops. While genes provide the framework, epigenetics provides the flexibility. It what bends and what shapes the backbone to fit the environment and the changes in the environment. And that's the reason why our health, resilience, or risk to disease can be so different, even with an identical DNA.
Epigenetics is constantly influencing our health and disease development, such as cancer. You mentioned DNA methylation. Do you see epigenetics influencing public health in the future? Like, do you think there's a potential to reshape disease prevention or early detection strategies?
Absolutely. I believe that epigenetics will reshape the public health. And by moving from treating disease, everybody is talking about treating prevention. Prevention is very important. So epigenetics allows you to prevent disease. It gives you the potential to prevent disease. In many cases, DNA methylation appear years before any symptoms. It's like a smoke before a fire. And that makes epigenetic testing a powerful early warning system. Even a person feels completely healthy, you can see the smoke. So, and the second major impact is personalization. As I said, that two people with the same genes, they can respond differently to the diet, lifestyle, medicine. So epigenetics explains those differences. And the prevention and treatment can be tailored to the individual, not just average patient, as we know how the medical system in general works, right? So the epigenetics help you to personalize the treatment. Honestly, I imagine a doctor's visit, and in addition to your blood work or blood pressure, kind of epigenetic passport. It's a health passport. It will be essential part of the diagnosis. The genes tells you about the fixed risks. Epigenetics shows what is the current health situation, and more importantly, reversible risks. You know, that's the opportunity. It's only a predictor of disease. It's not only the predictor of disease, but it's also a tool for intervention. So To me, the biggest public health impact is detecting risk or disease early, personalized prevention, and giving the people the chance to improve their health.
So how far are we from that point? What do you see? What steps are next for having this connection between epigenetics and public health?
I mean, I think it's a coming. Many companies actually involved, a lot of epigenetic companies. As you know, one of the major platform of studying DNA methylation provided by Illumina evolved significantly from 27,000 CPGs. Today we are talking about close to 1 million CPGs that can be used in array. That shows how this field is hot and how this field is important. The major problem in the field of DNA methylation is accuracy of the test, because the array technology is great, but there are many problems with array technology. There is a lot of correction that you need to do, the batch correction you need to do. And the question is, if you do the second test on another array without knowing it's the same person and without doing batch correction, you will see technical noise, but not biological. So, and I think the companies need to focus more on accuracy of the test. Genetic is easy, right? You measure the DNA occurrence of the SNP, right? And you don't need to deal with a conversion, very harsh chemical reaction to convert DNA, where you lose almost 90% of the DNA. Here you move to math. And sometimes in DNA methylation, 2 plus 3, you expect 5, but sometimes 5.5, it's a 4.5. It's very difficult to get exact number. So the major problem is how to make 2 plus 3, 5. Once we solve this problem, I think it will be moved much faster. It's a matter of 5-10 years that we will see major changes in this. And for epigenetic profile, or epigenetic passport, another decade or so.
And maybe to add to that, using this DNA methylation profiles as a detection of someone's status, how linked do you think that is to someone ultimately developing a disease that needs to be treated? Do you think it's always kind of predictive of that, or is there some cases where, someone might have kind of a more, pathogenic looking DNA methylation profile, but, how linked is it to then developing a disease further down the line?
Well, we need to understand what's the normal profile of the healthy population. And that will require a lot of research. That will require a lot of clinical study to understand what's the normal range, right? How confident is the population is a normal in this population? The second question is, what does it mean when it's above that range? Is it pathological, or is just some, happens? And some of the marks are reversible, and we don't know are they pathological or not. Let's say the current stress, right? Current stress can change your methylation very fast, right? But then it's irreversible. There is no stress. In a few months, the specific regions in your genome will go back to the normal. The same is smoking. There is a known receptor, HRR, which is getting hypomethylated during the smoking or active smoking, right? So if you measure, you say, okay, there is some abnormality, but that's connected to receptor. Of course, smoking is bad, right? But in a few years, or even after a few months, when you stop smoking, you get your signal back. So of course, there is you need to understand that part of the genome is responsible from pathological. Of course, if you see the genes associated with the cancer, that's a smoke before the fact that you need to take care of this. If it's lifestyle changes that can be reversed very fast, then you need to just monitor it. So that's why the beauty of epigenetics, they are constantly changed. So you should monitor it. Again, it will require a lot of research, understanding what is the real pathology, what is the real smoke of the real fire, or what is the temporary, I'm stressed because of my exam, and then after exam, my methylation is going to the same level, right? It's a good question, but it will require a lot of research.
Now that we talk about epigenetics and its role in aging and disease and how important it is to have an accurate model, and also to understand that DNA methylation is susceptible to changes depending on the environment, I'd like to discuss one of your recent projects, that is EPH Public, a biological clock that uses only 3 CpG sites in a specific gene. So it's a big departure from traditional clocks that rely on hundreds or even thousands of sites. Could you tell us a little bit more about this biological clock and what inspired this minimalist approach?
Actually, I should clarify that we have actually two clocks there. And the one clock is EPH Public, which is free for any researchers using Illumina arrays. The equation is in the paper. And the second clock is more expanded. It's based on next generation sequencing. That includes additional CpGs from the same gene, all within a level 2 gene. The second clock is used more commercially or for any collaboration, clinical studies. Now, the main reason for developing NGS clock was that we wanted to move beyond microarrays, like Illumina EPIC arrays, right? Which I used all the time as a postdoctorate. Even I use it even now. These arrays, they suffer from batch effect, require a lot of corrections. With the targeted next generation sequencing, from another hand, you cannot sequence the whole genome cost effective, right? So you need to focus on very specific regions. And then we analyzed this array, a lot of array data. We found that these just 3 CpGs in LOF2 had almost a perfect correlation with the chronological age. And they also tracked very, very closely with other age-associated CpGs across the genome. Right? LOF2's role as a robust biomarker is known for many years. I think maybe thousands of publications supporting LOF as a strong age biomarker. And to best of my knowledge, actually, LOF is the most cited gene related to aging. So it has also, in addition, it has also clinical applications linking to very different diseases. So for us, LOF2 was the best candidate to develop NGS-based clock in this regard. And finally, when we compare it, this 3 CpG EPH public clock to much larger clocks, performance was almost the same. Sometimes slightly better, sometimes slightly worse, but overall there was no meaningful difference. So our thinking was, why use the bulldozer to pick up the end, and if you can just use tweezers, or you can use your fingers. That minimalist design makes the clock simple, it makes the clock cost effective, and you're still able to capture signals relevant to both first and second generations clocks, right? Already 4 generations of epigenetic clock. So not only chronological age, but also biological changes that are linked to disease and stress, for example.
So aside from the number of CpGs that the clock uses, what other characteristics would you highlight that make this clock unique among other epigenetic clocks?
The epigenetic age, it's a complex thing. And that's why we see different clocks. And sometimes the clocks, when the scientists publish study associated with epigenetic aging, they're always trying to see, okay, all the clocks, Horvath clock, Hannum clock, Grimm H1, Grimm H2, and compare. And they claim, okay, we were able to find the difference with this clock, but not with that clock. My understanding is that each clock can capture, first of all, capture not only common, but also specific CPGs. So it's not the question of which one is better, which one is more accurate, but I think it's taking different angles of the human health. So APH was able to detect stress. APH public was able to detect stress, and most of the clocks don't show much. That APH was clearly very sensitive to current stress level. That was very surprising. And it was like a snapshot, that how body is reacting. Also HIV, the clock showed about, if I'm not lying, a 12 years acceleration in untreated patients, and even tracked the reversal of aging signals once the treatment started. So not every clock could see that. But I'm not saying these clocks are bad. That clock captures HIV, other clocks capture something else. To me, shows that each clock has its own personality. Some are tuned to long-term damage. Other clocks, like ours, respond more to immediate biological stress. That suggests we shouldn't think of one, the best clock, but rather the different clocks may be completely complementary, and each capturing a different layer of biology. So maybe using together might give a more complete picture, and we may be close to epigenetic health passport that we were discussing.
You mentioned that the APH was tested in different conditions, such as HIV, for example. And were there any findings that surprised you? And do you think that, or is there any other condition that you like to test this clock on, or maybe other population?
Given that the APH public, the formula, the equation is publicly available, so they don't need, it's kind of closed algorithm. Every researcher testing different clocks, he can open the paper, take the equation, very simple equation, put these three CGs into the formula, and measure the different clinical conditions. So for me, honestly, the current stress was a big surprise, because I didn't see that effect coming from other clocks. The current stress was really age accelerating. And by the way, when we sell APH based on next generation sequencing to the customers, the people buy, or we do clinical study, we notice that the stress actually it's a major factor, and the stress management it's very important. Sometimes people are asking, what's the magic pill? My response, there is no magic pill. If you sleep well, if you rest well, if you can control your stress, which is quite difficult, I think, then you can do better job than any pill. Probably that can kill the industry of who sells the pills and magic pills of anti-aging, but I think the stress management is one of the most important things.
It's very impressive that this clock is sensible to a stress level. Do you think that it's related with the gene where those CPG sites are from, E-level gene?
That's the only gene that we are using. It is related. We don't know if it's a causal. What's the relationship between the stress and is it just a marker, or it's other connections? We don't know. But we know that these CPGs are getting hypermethylated, overmethylated when the person experiences the stress.
And does that change the expression level of that gene?
This is a very important question. I'd rather not guess without data, so I don't mislead. There are some papers, there are some studies showing changes in expression, but there is no strong evidence of that, how the expression is changed. And given it's that the CPGs are located on the boundary between gene allele and allele antisense, they go into different directions. So, and the question is, what these CPGs control? Are they controlling expression of antisense? That will be different effect. Are they controlling the promoter of the LOF2? That will be another effect. That's a question of academia, probably, because the industry doesn't care. Maybe it does, but you need to show clear evidences why this expression is important for predicting but that's a question, interesting question that can be asked in academia. What happened with expression on LOF2? And probably measuring not only expression of the LOF2 itself, but also the antisense. If the antisense is changed, what's the consequence, the downstream consequences of the antisense, right? So that's a whole hierarchy can be involved, different genes, when this, that's a trick of methylation happening in a regulatory region. You don't know exactly what happens.
Do you envision integrating EPH with other omics data, perhaps with transcriptomics or proteomics, or expanding it to capture additional tissue types?
EPH public is a one piece of the puzzle, right? And every biological clock is actually tissue specific, right? Your blood and saliva may not age exactly the same pace as your organs, as your brain, skin, or liver. So when we are talking about the epigenetic age acceleration, what are we talking about? Are we talking about your brain age acceleration, your liver brain acceleration, your kidney age acceleration? So the big next step, I think, and I think there are already some research, some studies, is understanding how much a simple blood or saliva test reflects what's happening in other organs. That's where integration becomes exciting, right? Different tissues and different types, transcriptomics, proteomics, even imaging that can add complementary information. I read recently a study, MRI studies. They study the brain that MRIs can predict biological age by measuring things like hippocampal volume. People whose brains look older at midlife were more likely to develop dementia and other diseases. So imagine combining epigenetic log with MRI to get a fuller picture of someone's health. And actually, we started to explore this ourselves. We used, that's really preliminary data, skin samples. We noticed that sun exposure accelerate EPH public level. So that's a clear example of environment leaving a tissue-specific signature in the skin. I think another important step in EPH is to develop longitudinal study, because following the same people over the years to see how EPH changes with the health, disease, or intervention. That will show whether it captures or not only the age, but the pace of aging and in real life. As you know, there are four generations of epigenetic clocks today, right? The original first generation, like a Horvath clock or Hannum clock, they were just built to measure calendar age, nothing else. They were best to predict age. Why you need this clock if you can just ask for the driving license, see the age, right? So it's meaningless. By the way, it was interesting to discover that actually the epigenetic changes with age, the goes be back to 60s in Moscow. The scientists were studying the salmon, that the level of DNA methylation drops as the fish age and the spawn. That wasn't, they didn't have array, pyrosequencing, or other technology. And that was the first real proof that methylation mark don't stay fixed, but change with the time. That was the pre-era of all the generations. And today, that early fishes study probably is the ancestor of all modern epigenetic ages. For me, combining clocks from different tissues, integrate them with omics, follow people over time, that's how we'll move probably from measuring age to truly mapping biology of aging.
There's also another product of yours, EpiLiver, that looks at hepatocellular carcinoma, and it's very important. It plays an important role in liver cancer detection. Could you expand a bit about that project?
Cancer detection is important. But now liver is called a silent killer. Why it is silent killer? Because it rarely develops any symptoms until the cancer is advanced. It's actually one of the deadliest cancers because it usually develops silently. By the time most of the patients are diagnosed, that disease is already advanced and treatment is very limited. As for other cancers, if the survival rate for dramatically higher if you detect early, but as it advanced, it's very difficult. Surgical removal or transplantation can give patients to a real chance to live longer. And the problem is that the current blood tests, like AFP, alpha fetoprotein, right, or imaging method, they miss many early cases. So that's the gap where EpiLiver is designed to fill. It's a high throughput DNA methylation test that looks at very specific changes in a cell-free DNA circulating in the blood, and it can identify tumors with a much higher accuracy, even at early stages. The goal is simple: to move diagnosis from delayed to early. And if we can detect liver cancer before symptoms appear, that can transform the outcome of the patients. It's not the question of the medical question. It's a question that should be asked to the governments. It's an economical question, because advanced liver is very expensive to treat. Surgery, hospitalization, long-term care, it's all add up. And screening with the biomarker testing has shown cost effectiveness similar to method like ultrasound plus AFP. In some scenarios, ultrasound is very limited. Biomarker-based strategy could be, could save more money than per the quality-adjusted life year. It's not about the science, EpiLiver. It's also detecting cancer soon and potentially saving the life and also the healthcare costs at the same time.
It's highly valuable to detect cancer in early stages, as you mentioned, so patients can have a better prognosis of their disease development and even treatments. How does EpiLiver achieve this? Are there any concepts involved in EpiLiver that help to identify this early detection, or how does it work?
The beauty of DNA methylation epigenetics, it's a smoke before the fire. Any methylation, and actually DNA methylation are early signals of cell transformation. And if you can catch them, you can actually detect them very early. So the idea of EpiLiver, it's a two-module system. We have HCC detect and HCC spec, right? So it's not just detect cancer, but to confirm it's really from the liver. And this is where these two markers sets come in. The EpiLiver combines these two complementary sets. Detect becomes the cancer in general. It looks for DNA methylation patterns that are commonly changed in tumors, in liver tumors. And if these signals are present in cell-free DNA, that suggests that cancer might be there. Now, HCC spec confirms that the signals are from the liver tissue. So it's a liver marker and not somewhere else. So it's like a fingerprint. It tells you not just that cancer is present, but that came from the liver. So if you like these analogies, the HCC spec and HCC detect together, it's like having a smoke detector and GPS locator in one test. Together, they give both sensitivity, specificity, meaning you can catch the cases, but also know that it's coming really from the liver. That makes the test much more useful in practice.
And how easy would that be to expand to like other types of cancer? If you like having this general detection and then, you don't see the spec.
Right. Well, actually, we have developed the pan-cancer test that we are currently validating with the different cancers. The pan-cancer test detects if there is a cancer or not. But you need any additional test, right? If, let's say, you detect cancer, but you don't know where it's coming from, then you use another set of markers and detect the origin of tissue, right? So in a liver, epi-liver case, we had a speck coming from the liver tissue. If if you develop other tests, right, and we have some tests that we're developing, breast-specific tissue, prostate-specific tissue, melanoma, skin-specific tissue, melanocyte-specific tissue, and so on.
My understanding is the pan-cancer test that you previously mentioned helps you to identify cancer, but does it also help you to identify the tissue of origin or to classify the cancer type, or an additional test like epi-liver is needed to confirm this cancer type? And is there a way that these tools work together?
Epi-liver is pan-cancer plus, because you need two tests, right? Epi-liver is a two biomarkers, two sets of the biomarkers. One is like pan-cancer that detects all the cancers without discrimination. But it has also another part that detects the tissue where it's coming from. So with the pan-cancer, you cannot discriminate. Is it liver or it's a breast or melanoma? But with another part of this, right? And epi-liver has two. One is pan-cancer, another is the tissue specificity. Pan-cancer itself, the set of the markers, they detect different cancers. And you don't know either it's coming from one tissue or from another tissue.
And is there a detection limit with that? If because it's a cell-free DNA,
right?
Is there some amplification there that you do in order to be able to detect?
Right.
Yes, so there's some tissues where you wouldn't get that much cell-free DNA going in the blood compared to others. So maybe there's some difference.
That's a very important question, and that's actually a limitation. The problem is not how good is the marker. The problem is how to get the cell-free DNA. The cell-free DNA is easier to detect at later stages. In early stages, once you catch enough, your marker will work. But when you don't detect, it's not because your markers are bad, because you don't get this cell-free DNA. So I gave you another analogy. If you go fishing and you have ocean, and if you fish close, somewhere, right, and you don't get any fish, it doesn't mean that there are no fishes. There are fishes, but there are other places. And then you need to, that's the fishing. So catching the cell-free DNA, which has a concentration of a few nanograms per ml, it's challenging. That's where I don't know if you read our another paper, where we expanded actually epi-liver into PBMCs. The PBMC, it's peripheral blood mononuclear cells, they solve challenges with cell-free DNA. cfDNA is only a tiny fraction of the total circulated cell-free DNA. After bisulfite conversion, you lose 80-90% of what left. So sensitivity depends on the tumor stage. That means in early cancer, when cfDNA is very low, detection can be unreliable. PBMC, on the other hand, it's abundant and always present, and regardless of stage. And so it gives you more stable material to work with. It avoids the problem of running out of DNA after conversion, because you have a lot of DNA. And also the challenge is, of course, is specificity. PBMC methylation markers must be carefully, you need to choose the way that they reflect liver cancer, not other cancers. So we have some preliminary data. They work very well, but we need to, the next studies, other studies are important to understand how specific are these markers in PBMC.
And what about implementing this type of test in different regions? For example, liver cancer affects regions that have like high hepatitis B prevalence. How does the implementation of EP-Liver is in these different varying levels of healthcare infrastructure?
I mean, that's a really important question, because liver cancer is much more common in regions like Asia and Africa, where hepatitis B is highly prevalent. Again, the challenge, it's not whether the test works, it does, but how to implement it in places with very different level of healthcare infrastructure. In high-income countries, it's relatively straightforward to set up the lab needed to run EP-liver test. In low resources countries or settings, building this kind of infrastructure is very expensive and also logistically very difficult. So one approach, for example, is to collect plasma in a deep freeze. But that requires centrifugation, reliable cold chain storage. But another option is, I don't know if you heard, there are stabilization tubes, like Streck tubes, which preserve blood and DNA for days without refrigeration. So it's like Streck tubes are like a thermos for samples. It keeps everything stable until it reaches the lab. Of course, you cannot, central lab, so you cannot keep for weeks. There is a limitation. I think a week. I'm not sure, but I think it's approximately a week. So the real opportunity here is this scale also. So how high throughput sequencing that we are using means that hundreds of samples can be processed in parallel. So in principle, entire population could be screened. But for that happens, first of all, government need to make early detection a priority, because treating advanced liver cancer, it's much more expensive than preventing it. Early stage surgery can push survival rate above 70%. 70% if it's catch early. And late stage, it drops to 15%. I don't want to sound too harsh, but treating late stages HCC is like patching a sinking ship. It's really like patching the sinking ship. It's very problematic. And prevention costs far less than rescue. So the payoff is very clear. At early stages, so that we can push survival, and the late stage drops down dramatically. That's why this shifting from late treatment to early detection matters so much. Focus from treatment to prevention. That's where tools like EP-Liver can actually make the biggest impact.
Thank you very much for sharing both of your projects and your experiences in academia and industry. It's been a pleasure hearing about your journey. And before we wrap up, what advice would you give to young researchers or students who are hoping to make an impact in epigenetics? It could be in academia or in the industry or even both.
If you're a student thinking about epigenetics, I'd say go for it. I think it's one of the most exciting areas in the biology right now, given that the flexibility that it provides to the backbone. It sits between the genes and environment, and it explains how our lifestyle, stress, diet, even our choices can shape biology without changing the DNA itself. So, and the field is wide open. Yeah, there is a lot of competition. There are many companies, and my first Professor Aaron Razin, Hebrew University, he was one of the pioneers in the field of DNA methylation. And when he was visiting the conferences, they called him Mr. Methylation, because he was the only one probably working on this field. Now this field is booming. This field is really booming. And that shows that it's not just a side effect of the genome, it's a very important part of the genome. There are so many unanswered questions still. And this field needs curious minds, people who are not afraid of complexity. It's true not only for epigenetics, but of the science. So for me, the challenges in science have been, we were talking about motivation. For me, the challenges in the science have always been like a fuel. They keep you moving. And if you're ready for that, epigenetics can give you a career full of discovery and real world impact.
Thank you very much for that valuable advice.
Thank you. Thank you so much.
Thanks so much.
Thank you for listening to Season 4 of the Circ Pod. If you enjoyed this podcast episode, you can check out our website for future episodes at thisisepigenetics.ca.